Hello everyone and welcome to lecture 21 of GPU computing. Today we're going to be talking about pinned memory and stream. So last time we spoke about intra-warp synchronization. We said that we can take advantage of the special relationship between threads that are in the same warp to synchronize between them quickly, and iTuda has built-in functions for that. In particular, there's two major categories of warp synchronization primitives. There's shuffle instructions that allow us to share data across threads that are in the same warp, so they can just share each other's register values with each other without having to go through shared memory. And there's voting instructions where we can, where threads can vote on something, or this is useful for checking which of these threads evaluate true of some predicates, or checking which threads in the warp are active on some branch. We started by looking at shuffle instructions, and we said there's different kinds of shuffle instructions. Shuffle, just shuffling, so you can get from a direct lane, so a direct thread, another thread in the warp, or you can shuffle up or down, or there's also a shuffle XOR kind of shuffle that's also useful in certain circumstances. And we applied shuffle instructions to reduction. So we looked at how when we had reduction, every iteration half the threads drop out. And then when we got to one warp, we in the previous implementation for this warp, we were actually going through shared memory and doing sync threads every time. But we realized that we actually don't need to do that. What we can do is we can simply use shuffle instructions to do a reduction tree within the warp without having to go through shared memory and without having to do any sync threads. We then looked at warp vote instructions, and we saw how we have different variants we have different ways we can vote. We can check if all the threads satisfy some predicates, or if one of them satisfies some predicate. There's a ballot where we can check which threads evaluates a predicate to true and which one is evaluated to false, and we get a mask that tells us that. And there's the active mask, which tells us which threads are active on a certain branch. And one thing that we saw that we can use warp vote functions for is whenever we want the threads in the warp to communicate, to have one thread do something on behalf of the others. So an example of that was if we were adding some elements to a queue, and we wanted to increment some counter, rather than having each thread increment the counter, we can have one thread in the warp increment the counter on behalf of all the others, and then each thread can figure out which slot in the queue it should take from among the ones that the leader thread allocated. And we saw the different steps for doing this. We assign a leader thread, then we figure out how many threads we need to add to the queue. Then the leader thread does the atomic operation, and then it broadcasts the result to the other threads. And then each active thread figures out where it stores its result. And we saw how to do each of these. We saw how we used active mask to figure out which threads are active, and the find first set intrinsic to find the first set bit in active mask in order to figure out which thread we want to assign as the leader. We saw how to use population count on the active mask to figure out how many bits are set, so that we figure out how much space we need to allocate in the queue. By the way, find first set and pop count are not intra-warp synchronization primitives. They're just intrinsics that each thread can call on its own, but they're useful when we are looking at when we are using intra-warp intrinsics, because we can apply them to the active mask to do all kinds of interesting things. So after we figure out the number of elements we want to allocate in the queue, we had the leader thread do the atomic operation, and then we used shuffle sync so that each thread in the warp gets the value from the leader thread to figure out where it should store its result. And then we saw how we can do some bitwise magic in order for us to figure out the position of each thread so that each thread can add its result. So the position in the queue for each active thread, so that each thread can add its result to the queue. So this is what we talked about last time. Any questions about intra-warp intrinsics before we talk about today's material? Is everything clear? Okay, so then today we're going to move on to a new topic, which is pinned memory. We're going to talk about pinned memory, and we're also going to talk about streams. So these are two related topics. So we'll start by talking about pinned memory, and then we'll talk about streams. So first, let's talk about pinned memory. What is pinned memory? So if you remember, we previously had vector addition code, and let me go So this is the vector addition code that we previously had. We basically had a vector add kernel, and what we did is we allocated memory for vectors. We copied the source vectors, we called the add kernel, and then we copied back the result vector, and then we did CUDA free to free the result. Okay, and I'm going to compile this and run it so that we get an idea. We kind of remember, how the time for executing this was divided. So here I'm going to write vecadd, and I'm going to run it. Okay, and as you can see, here I'm highlighting the copy time as well as the kernel time, just because we're going to be interested in focusing on copy time today. So as you can see, the CPU time took 76 milliseconds to do this. The GPU took much more, took 169 milliseconds. But what you can see is that the kernel time for the GPU actually just took 3.2 milliseconds. The total GPU time is dominated by what? As you can see, it's dominated by the copy time. It took 58 milliseconds to copy the vectors to the GPU. It took 94 milliseconds to copy them back. Okay. So when the vector is already on the GPU, obviously it's much better to do it on the GPU than do it on the CPU. But if the vector is on the CPU, the speed up that we get from doing it on the GPU doesn't really pay for the cost of doing the copying. And the question that we want to ask today is, can we optimize this copying? Can we reduce this copy time that we are incurring every time we copy things to and from the GPU? Okay, so let's see how we can do that. So this is the code that we wrote, and like I said, we're trying to see what we can do to reduce this CUDA copy time that we're spending before we do the vector addition and then after we do the vector addition to copy back. And to talk about how we can optimize this copying, let's first talk about what happens when we call CUDA copy. So what happens when we call CUDA copy is something called direct memory access, or DMA. What is DMA? So direct memory access, or DMA, it allows some hardware in some hardware unit in my hardware to access memory without involving the CPU. So whenever we say that something in the hardware has DMA access, it means that it can access the main memory of the CPU, or it can access some memory without involving the CPU. And copying between CPU and GPU actually uses DMA. And what that means is that when I copy data from main memory to the GPU, the CPU is not involved in this copy. The CPU doesn't load from main memory and then store to the GPU memory. It doesn't loop over these erased main memory and then load them and then go and store them to the GPU memory. What happens is there's something called a DMA engine, where when the CPU says it calls CUDA copy, it just calls it, and it can go and do other things. And this DMA engine is responsible for reading from the main memory of the CPU and putting the result in the GPU memory.
Okay. Professor?
Yes.
The DMA engine, is it in the main memory or inside the GPU?
No, the DMA engine is part. I mean, it depends. So there's all kinds of different DMA engines for different things. DMA in general is this idea of allowing some hardware to be able to access some memory without involving the CPU. This DMA engine that does the transfer from the main memory of the CPU to the GPU memory, I believe, is on the CPU. But obviously, you have to involve the GPU driver when you do this, but that also runs on this. Okay, this hardware unit, I believe, is on. Okay, so then, so what's the advantage of using DMA over having the CPU somehow, if the CPU somehow had access to GPU memory, to involve the CPU in the copy? What's the advantage of using DMA instead of using the CPU?
You can make specialized hardware that acts very fast, maybe.
Okay, so the DMA is specialized. It can probably copy much faster than having to involve the CPU in the copy. What else?
The CPU can do other useful work instead of waiting for memory.
Right, exactly. So I don't want to waste my CPU time just reading and writing. Okay. So what we can do is we can have the CPU can be utilized for other things while the memory copy is taking place. Okay, so while the Kuhnemann copy is happening, I can have the CPU do other things. Okay, so this is the advantage of using DMA. What's the disadvantage of using DMA? Well, not necessarily a disadvantage, but what's kind of what is something that we have to pay when we use DMA?
Maybe when you specify, give it an order, you cannot stop it, maybe easily. Maybe.
I mean, sure, that depends on how, that depends on the kind of access that DMA gives you, the DMA hardware, whether it gives you the ability to do that or not. I was looking more about what's the difference between accessing something from the CPU versus accessing it from a DMA engine.
The CPU is faster.
That's not what I'm looking for. What does the CPU do when it accesses main memory?
It issues a load instruction.
Right, it issues a load instruction. That load instruction is an address, right? The address is what kind of address?
It caches it, right? That's the thing, maybe.
Sure, it's going to cache it. But what kind of address does the CPU use to access main memory?
Virtual address.
At a virtual address. And what about a DMA? What's the DMA going to use?
The physical memory.
It's going to use a physical address, right? It's going to use a physical address. So the CPU uses a virtual address, and the CPU does address translation, right? When we do address translation, the software and the hardware that together do the address translation run on the CPU. The DMA engine does not have the capability of doing address translation. Okay, it doesn't have, it doesn't have the instructions to read from a page table and all these things. Okay, so the DMA engine is going to use a physical address when it reads from the main memory to write to the GPU memory. Now, what's the drawback with the DMA engine using a physical address?
It doesn't. It cannot reference the whole domain of the memory that's available.
No, it can. It can.
You can't
Well-
move memory around if you send something to the DMA.
So what you're saying is if the DMA is reading from something, you can't move that thing around, right?
Yes.
Right, exactly that. That's exactly the problem. So the DMA is using a physical address. If the memory that the DMA is reading gets swapped out, the DMA has no way of detecting that. Okay, a CPU can detect that because if something gets swapped out, when you come and translate it, you're gonna have a page fault, and then you're gonna swap it back in. Whereas with DMA, when it's reading from a physical location, a physical page, and then that physical page gets swapped by the operating system, the DMA engine has no way of knowing that. So it'll end up just continuing to read the same physical page, which now has new data. Okay? So we don't want that, obviously. We don't want the DMA to read the wrong data. So when we give the DMA a physical address to read, to start copying, what do we have to do with that, the memory at that physical address?
Lock it.
Right, we have to lock it. We have to make sure that that memory does not get moved by the OS, doesn't get swapped by the OS. Okay, and that is what pinned memory is. So as a recap, DMA uses a physical address to access memory. And because it uses a physical address, it cannot detect if the operating system swaps a virtual page with another virtual page at the same physical address. So if the operating system comes and puts a different page at the same physical address, the DMA has no way to detect that. So to avoid data corruption, what the OS must do is that any page, the OS should not be allowed to swap pages that are being accessed by DMA. So what we need to do to prevent the OS from accessing pages that are being accessed by DMA is that we need to lock these pages. So any page that's accessed by DMA needs to be page locked, or in other words, it needs to be pinned. Okay, so we have to allocate it as pinned memory so it doesn't get swapped away. Okay, so anything that's allocated as pinned memory, these pages are going to be marked. There's a special way of telling the OS, hey, do not swap these pages. Okay, so now this brings us to CUDA memcopy. So having now known that CUDA memcopy uses DMA and that DMA requires pages to be pinned, how do you think CUDA memcopy works? What does CUDA memcopy do?
It first locks the memory the whole memory it accesses and then reads.
So you're saying it unlock the memory and then it's going to do the DMA. It actually does something different than that. But the idea that the memory that we're copying from needs to be locked is correct. So when we allocate data, that data is allocated using malloc. Okay, so we haven't really done anything special to lock it. So we have to assume that the data can be swapped out. So what CUDA memcopy does is actually the following. When we copy from host to device, what the CPU is going to do is the CUDA runtime is going to have this pinned memory buffer that it's going to use. And what the CPU will do is the CPU is going to copy the data from the buffer that we want to copy to a pinned memory buffer. And then the DMA is going to copy the data from the pinned memory buffer to the GPU. And when we copy back, it's going to be the same, right? Because when we read from DMA, we don't want the page to be swapped out, but also when we're writing to DMA, we don't want the page to be swapped out. Sorry, when we're writing to the main memory using DMA, we don't want the page to be swapped out. So when we copy from device to host, the DMA is going to copy from the device to a pinned memory buffer, and then the CPU will copy from the pinned memory from the pinned memory buffer to the CPU buffer that was allocated by malloc. So as you can see, whenever we call CUDA memcopy, we're not doing just one copy. We're actually doing two copies. One copy is between the kind of the regular CPU buffer and the pinned memory buffer, and the other copy is between the pinned memory buffer and the device memory. And this, obviously, doing two copies instead of one incurs overhead. Okay? So what can we do to optimize the copies? What can we do to make the copies faster? Now that you know this. If I don't want to do two copies, I just want to do one copy, what can I do with my buffers? I can pin them, right?
We have the buffer immediately on the device and just like copy to it and read from it immediately.
So the pinned memory buffer is on the CPU, it's not on the GPU. So what we can do is we can have a pinned memory buffer on the CPU that has my original data, and then we just copy from that buffer, as opposed to having a non-pinned buffer and copying from that to the pinned memory buffer, and then having the DMA copy from the pinned memory buffer. Okay.
Professor, there is one thing I don't understand. You said at the beginning that the CPU doesn't do anything. It just calls CUDA memcopy and then it's done.
So what I said, I don't know if I said it that way. What I said at the beginning was that when you call CUDA memcopy, right, you initiate a copy and then that copy kind of happens. But what actually happens is what I'm telling you right now. Okay.
Oh.
So maybe what I meant by that is that there's a DMA engine that's taking care of the copy. So I told you that part, but I didn't tell you the part about the pinned memory, just because perhaps it was too early to introduce these kinds of things.
Oh, okay. Thank you.
Okay. Yeah, you're welcome.
Professor,
Yes.
I can't see what's the advantage of the DMA if the CPU is copying anyway. So, like, it's like we're doing more than we need to be.
Okay, good point. So in this case, another role of the DMA is to access the the GPU memory. Okay, because here the CPU does not have direct access to the GPU memory. Okay, so there's kind of a PCIe bus or maybe some other kind of interconnect, and we need to copy over that interconnect, and that's much slower, right? Copying to the pinned memory is much slower than copying over the interconnect to the GPU. Okay, so CPU doesn't have direct access to the GPU's memory, and that's why you have a specialized hardware that takes care of copying things over the interconnect between the main memory and the GPU.
Okay, thank you.
Question? Yeah, you're welcome. Good observation. Okay, so what we would like to do is we would like to make our copies faster, and to make our copies faster, what we can do is we can just our host arrays, allocate them directly in pinned memory, right? So pin our host arrays, allocate them in pinned memory rather than allocate them in a regular memory. Okay, so we can make the copies faster by allocating host arrays directly in pinned memory, and CUDA gives us an API to do that. So what we can do to allocate or deallocate host data in pinned memory directly is we can use CUDA malloc host. So this is just like CUDA malloc, but you add the word host, and what this tells CUDA is to allocate the data inside of a pinned memory buffer. Okay, and then we can use CUDA free host to free the data that was previously allocated inside of pinned memory. Okay. So it's just like CUDA malloc and CUDA free, but instead we're going to use we have the word host at the end. Okay. Now, since CUDA malloc host is so much makes my copies so much faster than doing malloc, using regular allocation, can I just go and allocate everything in pinned memory? Is that a good idea? Why don't I just go allocate all my data in pinned memory that I want to copy to the GPU?
How much space do we have in pinned memory?
I mean, if I have my main memory, it's the same pages, right? The same pages in my main memory. I can pin them or I can choose not to pin them. So there isn't really kind of a separate pinned memory capacity from the regular memory capacity.
You lose the flexibility of virtual memory and.
Right, exactly. So when I pin a page, I'm telling the OS that you cannot swap this page out. So if I go and allocate everything in pinned memory, right, I'm telling the OS that I want all my memory pages not to be swapped out. Well, what that means is that the OS is going to have less flexibility in swapping things back and forth. So that's going to degrade system performance because when the OS now only has fewer choices when it wants to evict pages, swap them. And then obviously I cannot allocate more pinned memory than the amount of memory that I actually have in the system. Okay, so you have to use pinned memory with a lot of caution. It should only be used for data that we are frequently copying back and forth between the CPU and the GPU. Okay, if we allocate too much pinned memory, this would degrade overall performance because we're reducing the virtual pages available for swap. All right. Now, in modern systems that have a lot of memory, if you have 128 gigabytes of main memory, but your GPU only has 4 gigabytes, for example, of device memory. The newer ones have more than that. Newer ones have 16 and 32. But I'm just kind of giving an example. If you have that, if your GPU has a small amount of memory, then maybe it's fine to use a lot of pinned memory because even if you use a lot of pinned memory, you're not going to be the amount of GPU memory that you have to pin corresponding memory for on the CPU is not that much compared to the amount of memory you have on the CPU. Okay, but in general, you have to be careful. Don't allocate everything in pinned memory. You should allocate the things where the copy overhead is really important. Okay, let's go and use these CUDA malloc host and CUDA free host in order for us to see what performance we get by allocating in pinned memory directly. I'm going to switch over here, and I'm allocating in the main file. So I'm going to open the main file, and here this is where I'm doing CUDA malloc for the host arrays. I have the X array, the Y array. I have two arrays. There's the Z on that I'm using for the CPU code, and there's the Z array that I'm using for the GPU. Okay, so what I'm actually going to do is I'm going to allocate pinned memory for both of them, right? Even though the GPU one is the one I care about because that's the one I'm going to copy back into, but I'm also going to allocate in the CPU because I want to show you what happens when we do that as well. So here, rather than allocating and using malloc, what I want to do is I'm going to replace the allocation malloc to use CUDA malloc host. So I'm going to get rid of all of this. Okay, and I'm going to write CUDA malloc host. And of course, I need to provide it a pointer to the pointer that I'm storing the pointer to the resulting allocation. So I will have a void double star cast, and I give it ampersand x. Okay, so this I'm going to give it a pointer to x that it knows where to allocate x. Okay, and I want to do the same thing for the rest. So here it's going to be y. Here it's going to be z underscore CPU, and here it's going to be z underscore GPU. Okay, so what this does is that it allocates the X, Y, Z CPU and Z GPU arrays in pinned memory. But I need to be careful because when I allocated pinned memory, I need to make sure I also deallocate it properly because I've pinned it. So I'm going to come down here where I was doing free, and instead I'm going to do CUDA free host. Okay. So again, we use CUDA malloc host to allocate, and it has the same syntax as CUDA malloc, and we use CUDA free host to deallocate. Okay, I'm gonna save this. I'm gonna compile it, and now I'm going to run it. Okay, and as you can see, the GPU time has improved substantially. It went from 169 milliseconds to 80 milliseconds. Okay, and the reason is that the copy time is much less. Here, the 58 milliseconds became 43 milliseconds. The 94 milliseconds for copying back became 20 milliseconds. Okay.
Why did the CPU time also improve?
Excellent observations. I was going to ask you that too. So why did the CPU time improve when I used pinned memory for the CPU buffer?
Oh, because we're not using page. The page is pinned now, so the OS is not playing with it anymore.
Right, exactly. So now our CPU pages are pinned, and what that means is that when I'm doing the calculation on the CPU, I'm also benefiting from the pinning because I'm not going to have any page faults while I'm doing my addition. All my pages are going to be in DRAM. Okay. So we improved the GPU time, but we also improved the CPU time. Okay. Okay, so any questions about pinned memory? Everything is clear? Okay, so having spoken about pinned memory, this here is the code that we just wrote. The next thing I want to talk about is stream. And to talk about that, I want to talk about parallelism at the system architecture level. So we've spoken a lot about parallelism. We've spoken a lot about data parallelism, right? Having different threads process different data in parallel. Today, I want to talk about parallelism at the system architecture level. This is more related to task parallelism. It's actually a form of pipeline parallelism. So when we have a typical system, we have a CPU, a GPU. CPU has main memory, the GPU has GPU memory, right? And usually what we do is we copy over, we compute on the GPU, and then we copy back. But the system is actually capable of simultaneously executing a grid on the GPU and copying from the host to the device and copying from the device to the host, okay? So the hardware that computes on the GPU is different from the hardware that copies from main memory to the GPU memory, and it's different from the hardware used to copy from the GPU memory back to the main memory. Okay? Since these are three different pieces of hardware, okay, or three different resources, let me be more general. Since these are three different hardware resources, okay, we can actually use these three things simultaneously. But so far, what we've been doing is we've been copying to the GPU, running on the GPU, and copying back. So each time we're only using one of these resources. We're not leveraging all three of them. And what we're going to try and do is we're going to try and leverage all three of them to fully utilize our hardware as much as we can. Let me show you what I mean by that. So when we are doing a vector addition previously, what we've been doing is we've been copying A to the device, and then copying B to the device, and then we've been executing a grid to compute A plus B and store the result in C, and then we've been copying C from the device. Okay, so here horizontal represents time. Well, if you take a look, when I'm copying A and B to the device, I'm actually not using the part of my system that runs on the GPUs. I'm not using the GPU itself, and I'm not using the resource that allows me to copy from the device to the host. And when I execute, so here during this time, my GPU is idle, and my resource that I use to copy back from the GPU to the host is idle. When I execute on the GPU, my hardware that does the copying to and from the GPU is idle. Okay, and then when I copy from the CPU, from the GPU back to the GPU itself is idle, and the part that can copy from the host to the device, from the CPU to the GPU, is idle. Okay, so what can we do to be able to utilize these hardware resources better?
We can start we can send it bit by bit and and start computing as we receive, and then output to main memory as we finish computing.
Right, exactly. So rather than copying all of A and B and then computing and then copying all of C back, we can copy part of A and B, and then while we're computing on that part, we can copy another part of A and B. And then while we're computing on the other part, we copy a third part of A and B, and all that time we're also copying back the parts that we're done computing. Okay, so in other words, what we can apply is pipelining. So we can pipeline vector addition like this. We can divide my A and B and C into segments. I can copy the first segment of A and B to the device. And then when the first segment of A and B are on the device, I can execute a grid to compute the first segments, A1 and B1. And then in the meantime, I can also be copying the second segment, A2 and B2, from the host to the device. Okay. And then when I'm done computing and I'm done copying, I can then go and copy the result of A1 plus B1 from the device back to C1. And in the meantime, here the copy of A2 and B2 is ready, so I can execute a grid to compute A2 plus B2. And in the meantime, I can also be copying the next segment, A3 and B3, from the host to the device. Okay? So as you can see, I can divide my array into segments, and every step I'd be copying one segment. I'd be parallelizing the copying of a segment with the computing of another segment with the copying back of the other segment. So actually, this is where the parallelism is happening. I'd be copying one segment while computing another segment while copying back another segment that is ready. Okay, so we're going to overlap copy and computation of different segments. Okay, and this goes on. So here, when I'm done, I can copy back C2 while I'm adding A3 and B3, while I'm copying A4 and B4 to the device, and I keep going. Okay. Any questions about this? Is it clear?
How many grids can we execute at the same time on the GPU?
It depends on the compute capability. So it depends on the architecture. Yeah.
So for example, can I start, for example, if it's small enough, can I start copying my data and executing many grids?
So in this case, what's really going to dominate the critical path of this pipeline is actually the copying. Okay, so parallelizing different grids is not really beneficial. But yeah, yes, I mean, hypothetically, you can run different grids in parallel on the GPU. This particular example, that's not very useful. But in general, yes, you can run multiple grids on the GPU in parallel. But you know, if you were going to run these in parallel, you might as well put them in the same grid, right? Okay. So then, in order for us to be able to apply this pipelining, to do this kind of pipelining, what we need to do is we will actually need to make these copies asynchronous. So we're going to need to be able to kind of start off a copy and then let it go, not wait for it, and be able to do a grid execution and copy back all kind of in parallel without having to wait for any of them. Okay, and this introduces the topic of stream. Okay, so the parallelism between grids and memory copies can be achieved using stream. Okay, and we're also going to use asynchronous copies. So the ways, what streams are in CUDA, you have these streams that contain different tasks that need to be executed sequentially. Whereas if I put tasks in different streams, they're executed in parallel. So tasks in different streams are executed in parallel, and tasks in the same stream are serialized. Now, by default, if I don't specify a stream, what's going to happen is everything is going to go into the default stream. Okay. So if I specify multiple CUDA-MEM copies, by default, all these CUDA-MEM copies will go into the same stream and they will be serialized. Okay, same thing with kernels. If I kernel multiple CUDA-MEM copies and multiple kernels, all of these will go in the same stream and they will be serialized. If I want different CUDA-MEM copies and different kernels to execute in parallel, right? So for example, on this previous slide, if I want this CUDA-MEM copy back to execute in parallel with this grid, to execute in parallel with this CUDA-MEM copy to the device, these need to be put in different streams. By default, if I just call them without specifying a stream, they all go into the same stream, so they will be serialized. Okay. So to put them in different streams, what we will we're also going to need asynchronous mem copies. So to be able to overlap mem copies with the host execution, we're going to need to use asynchronous mem copies, because by default, the CUDA-MEM copy is not asynchronous. Okay. So having asynchronous CUDA-MEM copies, it allows the host to go and wait for a copy to finish so that it can. Sorry, it allows the host to proceed without waiting for a copy to finish so that it can perform other things. Okay, so when the host calls the CUDA-MEM copy, it doesn't need to wait for it. It goes and it can go and call other kernels, call other CUDA-MEM copies. So that's the benefit of using asynchronous memory copies. Okay, let's see how we can do that. How can we create streams and how we can call asynchronous memory copies? The way to do that is using the following API calls. To create a stream, we can call CUDA create stream and provide it with a pointer to an object of type CUDA stream_t, and this is where the create stream will put the information, the handle for the stream, so the identifier for the stream that we just created. Okay. To create an asynchronous copy inside of a stream, we can use the same CUDA-MEM copy API, but with an async at the end of it. So it looks the same as the CUDA-MEM copy API, but it has an async at the end of it. Okay, so it's called CUDA-MEM copy async. And what this CUDA-MEM copy async takes as a fifth argument is a CUDA stream. By default, if we don't specify the stream, it's going to go into stream 0, which is the default stream. Okay. However, if we want to put the CUDA-MEM copy to a specific stream, we can specify what stream we want by providing this, kind of a stream handle that we created using the CUDA stream create. Okay, and then finally, if we want to launch a grid inside of a specific stream, we call the kernel like this. The kernel configurations, we've seen two. We actually saw a third as well. But we've mostly been using these two so far, the grid dimension and the block dimension. Okay, but the grid configurations actually take other optional configurations, and these include the amount of dynamically allocated shared memory that we want to have per block. This is by default 0. And then the fourth optional argument, or the fourth argument, which is optional, the fourth configuration, which is optional, is the stream that we want to put the kernel in. And again, by default, if we don't specify a stream, it goes into the default. Okay. So what we would like to do is we would like to divide our input into pieces, into segments, and then have a separate CUDA copy to the device, a grid launch, and a CUDA copy from device for each segment that goes into a different stream. And let's see how to do that. So I'm going to switch back to my code. This time I'm going to open my kernel code. And here in my kernel code, I have my vector addition kernel, which I'm not going to change. This time I'm going to be working on the host code. So in the host code, I do CUDA malloc. Okay, and then over here, which is the interesting part, I'm doing CUDA copy to the GPU, and then I'm calling the kernel, and then I'm copying back. And what I'd like to do is I would like to divide my input into segments based on how many streams I have, and do a separate CUDA copy, vector addition, vector add kernel, and CUDA copy back for each segment. Okay. So let me start by creating the different streams that I would like to use in order to process these segments in parallel. So I'm going to first set up my streams. To set up my streams, first let me pick a number of streams that I want. I'm going to create an integer, unsigned int num streams. Okay, and I can define a different number of streams. I'm going to use 32 streams, for example. So I'm going to have 32 different streams. Then I'm going to divide my input into 32 different segments and have a segment be done in each stream. Okay, so I want to create 32 different streams. So I'm going to first declare 32 different streams. So I'm going to do it like this. So CUDA stream _ t is the type of a stream. If I want to declare one stream, I can do it like this. If I want to declare 32, I can simply provide 32 or num streams over here as so this will be an array of 32 different streams. Okay. Now to create a stream, I need to use the CUDA stream create API call. So I'm going to loop over my streams and I'm going to create them. So I'm going to write for unsigned int s equals 0. So here s is going to be the index of the stream I'm creating. S is less than the number of streams plus f. And then for each of these, I'm going to call CUDA stream create. And here CUDA stream create just takes one argument, which is a pointer to the stream that I want to create. So here I'm going to provide it with a pointer. So I'm going to take the address of the stream s. Okay. So now what I've done is I've created 32 different streams. Clear so far? Any questions?
Why did you choose 32 streams?
I just picked it arbitrarily. It's I decided it was a good number. You can use 8 streams, you can use 16 streams, you can use as many streams as you want.
Okay, so
it's like making forks, like doing multiple processes asynchronously.
I mean, the idea, when you fork, you're creating different CPU threads. So here we're not really creating different CPU threads. We're creating different queues in which we're going to put the operations that we tell the GPU to do, and we're going to create these different queues, and we're going to put each thing we tell the GPU to do in a stream. Okay, so if I want the GPU to be able to run different grids in parallel, okay, so I have multiple different grids I want them to run in parallel, or multiple different CUDA copies I want them to run in parallel. By default they will be serialized because they will go in the same stream. If I want them to be parallelized, I need to put them in different streams. Okay, have I answered your question?
Yes, yes. I thought we were multi-threading on the CPU. But,
no, we're not multi-threading. We're using one CPU thread, but we're putting commands to the GPU in different streams so that to tell the GPU that hey, these things can be done in parallel. Now, another way to do it is to have multiple threads on the CPU and have each thread create its own stream and send its own commands to the GPU. So in that case, we would be multi-threading. So that would be another way to do it. And typically, you know, if different threads are running on the CPU and each one of them is using the GPU for its own computation, we would typically want to create different streams, one for each thread, so that the threads can use the GPU independently. Okay, so that's I'm glad you asked that. Okay, so next thing we want to do is we want to break up the input into different segments. And we want to loop over these segments and have a CUDA copy, a vector add kernel, and a CUDA copy back for each one of these segments. Okay. Oops. What I want. Okay, so here next we're going to stream the segments. All right. So my number of segments is going to be same as the number of streams. So I'm going to just create a variable num segments for convenience, and it's going to be the same as the number of streams. Okay, and the size of my segment is going to be the size of the input divided by the number of streams. So the segment size is going to be equal to n over the number of segments, and of course n may not be divisible here. N is the size of the whole array that I'm adding, but n may not be divisible by the number of segments. So in this case, what I want to do is I want to do a ceiling. So I'm going to do that by doing n plus num segments minus 1 over num segments. Okay. Now I can loop over my segments. I'm going to write for unsigned int f equals 0, s is less than the number of segments plus s. And now for each one of these segments, I would like to copy it to the GPU, call the grid, and copy it back. And by putting them in different streams, we will get the pipelining that we are interested in getting. Okay, let me first figure out what part of the input each segment is going to process. Okay, so I'm going to start by finding the segment bounds. Okay. So the segment, I have the segment size. Okay, so every segment is going to start at the segment index times the segment size, right? Segment 0 is going to start at 0. Segment 1 is going to start at 1 times segment size. Segment 2 is going to start at 2 times segment size, etc. So the start of the segment is going to be at s times segment size. The end of the segment is going to be at the start of the segment, right, plus the segment size. However, the end of the segment could be out of bounds, right? So for the very last segment, maybe n is not divisible by the number of segments. So I need to make sure that for the last segment, I handle it properly. So I'm going to do a minimum between start plus segment and n. So here, if the end of the segment is less than n, then I just, so it's the start plus segment size less than n, then I take that as the end of the segment. Okay, otherwise I'm in the last segment, so I will just use n as the end of the segment. Okay, and what that means is actually different segments are going to have different size. In particular, all the segments are going to have segment size as their size, except for the very last segment, it's going to have a smaller size. Okay, so I'm gonna have another variable n segment that tells me the number of elements in the segment, and that's going to be n minus start. Okay, so for all segments, n minus start is going to be start plus segment size minus start. So n segments is just going to be segment size. But for the last segment, n minus start is going to be the size of the last segment, which I could have also computed as n modulo the segment size. Okay. So now for each segment, I know where it starts, I know where it ends, and I know the size of that segment. Now I can go and modify my copies and my vector addition kernel and my copy back in order for me to take care of copying that segment to the GPU, computing on it, and copying it back. Now, before I do that, I wanna get rid of this synchronization. Before I was synchronizing after every CUDA copy, after every vector addition kernel, after every copy back. I don't want to do that because I want to be doing all these things in parallel. So I'm going to move the CUDA device synchronize outside, and I'm going to time the whole thing. I can no longer time individual copies because all of this stuff is happening in parallel. So I'm going to move the timer outside. Okay, and I'm going to copy how much the whole thing takes with the copies and the kernel combined, because now the copies and the kernels are happening in parallel. Okay, so now here I'm going to synchronize at the end, and this time is going to be the copy to and from the GPU as well as the kernel time. So it's the copy to flash from GPU and kernel time. Okay, and I'm going to get rid of these other timing things. Okay, so now what I want to do is I want to modify CUDA copy, the vector addition kernel, and the CUDA copy back in order to use asynchronous CUDA memory copies and use a different stream for each segment. Okay, let's start with the CUDA copies. So for the CUDA copy, I'm going to use CUDA copy async, and I'm going to provide the stream at the end. Okay, so here with the CUDA copies, I want to use CUDA copy async. Okay, and I'm going to provide the stream at the end, so that's going to be stream of S. Stream of S. Okay, and of course, I'm no longer going to be copying the entire input. On each iteration, I just want to copy the segment that I'm interested in. Okay, so here, the segment starts at, this is going to be x underscore d plus start, and y underscore d plus start. Okay, actually, there's a kind of a neater way of writing this that I personally prefer, which is I want to return the address of y of d start. Okay, that just makes it clear what's going on. These are two different ways of writing the same thing. Okay, same thing here. I'm copying this. What this is saying is that my x of d, I am copying at an offset of start. That's where I'm gonna start copying. And where I'm copying from is also going to be the same thing. I want to copy from x plus start. Reminder: start is where the segment starts in the entire array. So here I'm going to copy from x of starting at x of start. And here I'm going to copy starting at y of start. Okay, and then the amount that I'm going to copy is no longer n. It's going to be the size of the segment itself, which is n segment. And n segment is going to be equal to segment size for all of the segments except for the last segment. So here, this is going to be n segment, and this is going to be n segment. Okay. Same thing for the copy back. I'm going to use an asynchronous copy back. Okay, I'm going to provide it with the stream to put the copy back in. Okay, and I'm going to provide it with where to start copying from. Sorry, where to start copying to and from. So here it's going to be the address of z of start and the address of z underscore d of start. And the amount I'm going to copy is going to be n segment as opposed to the entire n. Right? Clear?
Dr. Bus, a question.
Yes.
So for the CUDA memcopy async, the way it works is that it starts the operation, but doesn't wait for it to finish, and it starts it, but continues execution of the remaining code.
Right, exactly. So it calls CUDA memcopy async, and then it comes down here and doesn't wait for the CUDA memcopy async to finish. It just comes down here and calls the vector addition kernel, and it doesn't. And vector addition kernel by the kernel calls by definition asynchronous, so it doesn't wait for the vector addition kernel to finish. It just comes down here, does CUDA memcopy async, and then it's going to go back and start with start calling CUDA memcopy and vector addition for the next segment without waiting for the previous segment to finish.
Okay, and what if for some reason the CUDA memcopy didn't, like one data element didn't finish for the vector addition kernel to start?
So
like
CUDA memcopy, so these CUDA for the same segment, these CUDA memcopies and this vec add kernel are going to go into the same stream.
Okay, okay.
So they will be serialized by that stream. This vec add kernel is not going to start before the CUDA copy complete. Okay. However, it's going to be ended because it's going to be in the same stream. However, it's going to be independent of the CUDA copies that are going to be called in other iterations of this loop that are going to be put in different streams.
Okay, got it.
Good question.
Okay.
So we'll see. So that brings me to the vec add kernel. So the vec add kernel, I will also want to put it in the same stream as the CUDA copies that correspond to it. Okay, so here I'm not going to dynamically allocate any shared memory, and I'm going to provide the stream. That's going to be stream of S. So now for the same stream, the CUDA copies, okay, and the kernel and the CUDA copy back are all going to go into that stream. So everything that's called in iteration 1 is going to be serialized with respect to each other, but they're going to be completely independent from everything that's being called in the other iteration. Okay, clear? And of course, now for the yes, question?
Yeah, there's a typo for the unsigned end. Should be a question mark, the first one, I think, after the condition.
Yes, thank you. Thank you. Right here. Yes, this should be a question. Thank you. Okay, and then here now again, I want to give each vec add kernel its own segment. So I'm going to give it, rather than giving x of d, I'm going to give it the address of x of d start, the address of y of d start, and the address of z of d start, and I'm going to give it as well and second. Okay. Is it clear to everyone what we just did? Any questions about this code that we wrote? So we're basically looping over the segment, and for each segment, we are enqueuing a CUDA copy to the device, a vec add kernel, and a CUDA copy back in the same stream, so that these will be done sequentially. However, we're not going to wait for any of these to finish. We're going to move on to the next segment and also enqueue its copies and kernel call. And we're going to do that for all the segments. So now I have all my streams loaded with CUDA copies and kernel calls. And then I'm going to sit here and I'm going to wait for all of them to finish before I move on. That's what CUDA device synchronized. Clear? Any questions?
Yes, if you want to measure the kernel time only, how can we do that?
So if you want to measure the kernel time only without interfering with the performance, you can use something called CUDA event, where you can actually add an event into a stream. And what the event does is it basically takes a timestamp of when something in the stream started or finished. Okay, so you can add a CUDA copy to a stream. You can add a kernel into a stream. You can also add an event to a stream. And by taking the time difference between different events, you can tell how long something in a particular stream. Okay, but we're not looking at today. We're not going to look at the events, but you can look at those. You can look those up in the documentation and read about how. But that's a great question. So if I want to look at how long a particular operation in a particular stream took, I can use CUDA events to do that. Okay.
Professor?
Yes.
Yeah, sorry. I was wondering, this will only shave off time from the kernel time, right? Since in most cases the memory is the bottleneck. Like the gain time will only come from a reduction in the kernel time.
So what we're going to be doing is we're going to be overlapping the copy time with the kernel time. So the copy to time with the kernel time with the copy back time. So whichever takes the most time is going to hide the latency. This is how pipelining works, right? The state that dominates that has the highest latency in the pipeline is going to be what dictates how long something takes in your pipeline. So yes, whatever takes long, in this case it's the copy to, that's what's going to dictate how long this whole thing's going to take. And we're actually going to run the profiler to visualize all of it. So kind of hold on, you'll have a very visual answer to your question.
Okay, thank you.
Yeah, you're welcome.
Professor, yes, a quick question. So when we enqueue some task, let's say CUDA memcopy async, does it, like if we have the resources available, does it just start?
Yes, it goes into
Or-
the queue and it will start if the resources are available, of course.
Okay, and then the rest of the waiting will be just waiting for the resources to become available, right?
Right, exactly. But I can loop through and add my tasks to my stream faster than my stream can complete them.
Yes.
That's why when I
yes.
have this loop, I loop over all the segments and I put everything in the streams, and then now I just sit here and wait for all of them to finish. In the meantime, I could have the CPU go and do other things if I want. Maybe I can have the CPU add its own part. Maybe I can assign one of the segments to the CPU itself and have the CPU add part of the segment rather than sit here and wait and do nothing. Okay.
Okay, thank you.
Yeah, you're welcome. All right, so let's run this and see what kind of performance we get. So I'm going to compile. Okay, and I'm going to run. So as a reminder, the GPU time previously took 80 milliseconds. Now when we run, it takes 60 milliseconds. Okay, and here what you can tell is that the copy to, from, and kernel time. So remember, we're timing them all together because we can't separate them. Now this is taking 49 milliseconds, which is a little bit more than the copy to time. So here, the total copy to time was 43 milliseconds. The total kernel time was 3 milliseconds. The total copy back time was 20 milliseconds. Okay, so this whole thing was more than 60 milliseconds. Okay, now it's taking 49 milliseconds. You can tell that this is quite close to the copy to time. So we hide the latency of these other phases with respect to this. Okay. And let me kind of show you that visually. What I'm going to do is I'm going to profile this code in order to kind of show you what's happening in the timeline of the code. So I'm going to call nvprof. I'm going to output a timeline. Okay, so I'm going to call back add, and this time I'm going to call it with nvprof. Okay. And I'm going to do the same thing. I kind of saved a version that does not use the original version that doesn't use streams. I'm going to compile that. And I'm also going to call it with nvprof. Okay, so now we have a timeline for the one without streams and for the one with streams. So now let's go to the visual profiler and open these timelines and see what they look like. So we switch to the profiler, and now what I'm going to do is I'm going to import the timelines that we just generated using nvprof. So I'm going to import, next. We're going to get the timeline data. Okay, first we're going to get the timeline data for the one without streams. Okay, finish. Okay, so now here, this is the beginning where we were doing the CUDA device synchronize at the beginning and the CUDA malloc host and these kinds of things. So we're going to go to the end over here. Let me zoom in a little bit. Okay, so this is where everything's happening. So as you can see, this is the version without streams. I have a CUDA memcopy host a device, and then a CUDA memcopy hosts the device, and then I have my kernel call that's executing, and then I have CUDA memcopy device to host. And notice how here, now you know what this means. Here it tells you the stream in which everything is being executed. So here it organizes things by the kind of operation that's happening. Down here it tells you the stream that everything's being executed. As you can see, it says that all this stuff is happening in the default stream. So here the hosted device, and then the grid execution, and then the device to host, all of this is happening in the default stream. Okay. Now let's go and import the version that we used with streams in it, with multiple streams. I'm going to import. Next. I'm going to browse. This time I'm going to go to the version we implemented that uses streams. I'm going to get the timeline for this. Okay, finish. Okay, I'm going to zoom in again. Okay, and as you can see, let me zoom in a little bit more. So there's a little bit of a delay. There we go. So as you can see, our memcopy hosted device, now it's all these little pieces. See? And our memcopy device to host is all these little pieces. Okay, and our compute, our grid calls is all these little pieces. And you can tell that the copying from host to device and the copying from device to host and the compute is all being done in parallel with each other. Okay, so we've effectively hidden the copy from device to host and the compute behind the copy from host to device, which is what dominates performance. And if we want to see this in kind of this as a stream in the stream view, let me expand this a little bit. So now you can see what's happening inside of each stream. So in each stream, I have a CUDA memcopy, and then a grid. So I have two CUDA memcopies, and then I have a grid call, and then I have a CUDA memcopy back. But as you can see here, these CUDA memcopies are, and then the grid call. This grid call is overlapped with the CUDA memcopies of this other stream, and then this grid call is overlapped with the CUDA memcopies of this stream. Okay, and this grid call is overlapped with the CUDA memcopy of this stream, and it goes on. Okay, and then we come back here, and you'll see how our CUDA memcopies are all overlapped with other grid calls and CUDA memcopy back. So here you can see how this CUDA memcopy back is overlapped with the grid call of this stream, and it's overlapped with the CUDA memcopy 2 of this stream. Okay, so again, all the CUDA memcopies are overlapped with the CUDA memcopy back and the grid call. So we've effectively pipelined our operation so that we hide the latency of the grid, or most of the latency of the grid execution and the copy back behind the copy to the device. Okay, is it clear? Any questions about this diagram?
Professor?
Yes.
The interconnect that gets data to the GPU is different than the one that brings data back from the GPU?
No, it's the same interconnect, but it has different lanes.
And these lanes don't there's no lane that can do both.
Yes, you have lanes that copy from the CPU to the GPU and lanes that copy back.
Oh, I see. So that explains why we can save on the device to host, right? Because had they been the same, then we couldn't have pipelined both in the same time frame, right?
Right. If the copy to and the copy back are using the same hardware resource, then you wouldn't be able to parallelize the copy to and the copy back. But because they use different hardware resources, that is why you can parallelize them.
Okay, I see. Thank you.
Yeah, you're welcome.
Doctor?
Yes?
I think PCIe has a lot of lanes, and for the GPU here, for NVIDIA GPUs, we use NVLink, right?
So it depends. It depends on the kind of CPU you have. Some CPUs support NVLink and some don't. So if your CPU supports NVLink, then you can use NVLink. But the older CPUs and also even some current CPUs, they don't all support NVLink. So if they don't support NVLink, the more wider standard is PCIe. But if you do have a CPU that supports NVLink, NVLink is usually faster.
Okay, and one more thing, we have multiple lanes, right? Like not only one for copy to and one for copy from. So we can have even multiple streams running at the same time, right?
You mean there's multiple lanes? The PCIe bus has multiple lanes for copying, right? So multiple of these lanes will be used to copy to, and multiple of these lanes will be used to copy from. But you shouldn't confuse the PCIe lanes with the stream, because one stream could be using multiple lanes while doing the copy.
Okay, okay.
Okay.
Professor, one question about memory in the GPU. So instead of copying to and from, can't we take the GPU memory and make it act as a cache?
So there's something called unified memory, and we will talk about this in a later lecture, where you can kind of allocate something in the CPU and then access it from the GPU. And this gives us the convenience of not having to do any of these CUDA-MEM copies, and that's widely used. We don't show it to you just because we want you to understand what's going on under the hood. But now that you understand this, later on I'm going to show you how to use, or I'm going to talk to you about unified virtual memory, where you can just allocate things on the CPU and run them on the GPU and access them on the GPU. But underneath the hood, depending on the architecture you have, what might be happening is what we have over here. Something will get copied from the CPU to the GPU memory on demand or backwards. There are other architectures where they integrate the CPU and the GPU on the same chip, so they actually access the same memory. But for the GPUs that are kind of large and have very high performance, these are usually discrete and they have their own independent memory from the CPU. But we can kind of simulate the feeling of them having the same exact memory using unified memory.
Okay, thank you.
Okay, yeah, you're welcome. Okay, so now that we've seen things in the profiler, let's switch back to the slides. So these are the API calls, again, that we use to create a stream and then do the asynchronous memory copies. And this is the code that we wrote to do the streaming. And then this is an illustration of the profiling results that we got. I know they're a little bit different from what we saw in the profiler, because I generated these on a different machine than the one we are using during the lecture. Okay, and with that, you can read more about what we covered today in chapter 18 of the textbook. Does anybody have any final questions before we end? Okay, if not, then that's all for today, and I'll see you next time. Bye, everyone.